In today's module, we're going to start a new segment where we're talking about water. And the first thing I want to emphasize is that water is different from some of the other things that we've talked about, such as fossil fuels. So there's a limit to the amount of petroleum or coal or natural gas that is in the earth. Sometimes we are able to push those limits through new technologies such as fracking. So our concept of the available reserves has increased in the last few years because of fracking. So we now think there's more natural gas that is available to us, more petroleum that's available to us than what we thought a few years ago. But even with these new technologies, that's not making any more petroleum. And when we use the petroleum, we destroy it. We convert all the carbon atoms in oil into carbon dioxide atoms, so the petroleum is no more. So even if there is an extension in terms of what we consider to be the lifetime supply of coal or petroleum, there's still a limit to how much of the fossil fuel that we have. But that's not the case with water. We have as much water on the earth as we've ever had, at least going back into human dimensions, not talking about the very early ages of Earth, millions or even billions of years ago, before there was surface water on the Earth. But at least in the human lifetime, humans aren't doing anything to destroy water. There's as much water as we've always had. The problem is that the water isn't always where we want it to be. So humans are located in certain places and the water might be located in other places, and so we don't have access to the water that we might want. And the other problem is the water isn't always in the form that we want. So the water can be salty, for example, in the oceans, that makes it essentially unusable for us unless we treat it in some way. Or sometimes we're polluting water with contaminants such as solvents or gasoline, something like that, to make the water unusable. But the net effect is that we still have as much water as we want. So let me go to the next slide here and we'll talk about where water occurs. That is the way in which water occurs on the surface of the earth. And here you can see that the majority of water is in the oceans. 97% of the water on the earth is tied up in the oceans. And unfortunately, that makes it pretty unusable for most of the things that we want to do as human beings. That doesn't mean that we can't take the water from the oceans and treat it and make it usable, but it's expensive. It takes a lot of energy to make fresh water out of ocean water. We know how to do it. We have the technologies to do it, but it's not cheap and requires a lot of energy. So the unfortunate thing here is that the vast majority of water that's on the earth is not really usable to us in the form that we find it. Only 3% of the earth's water supply is fresh water. And so if we take a look at the fresh water and how that's divided up, of that 3%, 70% is tied up as ice or glaciers. Now, unfortunately, with climate change, that percentage is dropping. We're losing some of the world's supply of glacier ice, and as that ice melts, it runs into the oceans and becomes salty. So the percentage of the world's supply, ultimately, if those glaciers were to melt, the amount of fresh water that's available on the earth could actually decrease. Instead of just being 3%, it might be 2% or 1% if we lost those glaciers. But the problem is that fresh water tied up as glaciers really isn't too useful to us. Now, there are some very rich, oil-rich countries in the Middle East that have decided that one possible solution to their water problem might be to hook onto an iceberg and tow that iceberg to the Middle East, and then they can use that fresh water, and they've done some calculations trying to figure out whether it's cheaper to do that or to do the desalination process for the ocean water. But there has been some attempts to use this glacier ice as a water supply, but for the most part that's not the case. when water is tied up as ice or glaciers, it's really not too usable to us. So 70% of that 3% of fresh water is in a form that's not real useful to us. 29%, so now we're up to 99% of the fresh water, 29% of that fresh water is in aquifers. That is, it's groundwater. It's underneath the ground. Now, sometimes that groundwater is relatively accessible to us. We can drill a well. It doesn't have to go too deep, and we can withdraw that groundwater. So groundwater does represent a source for us to use, but sometimes that groundwater is inaccessible. It's there, but it's so deep and so difficult to bring to the surface that it really doesn't help us. So only a fraction of that 29% of groundwater is really accessible to us as humans. And then what's really interesting here is that only 1% of the Earth's fresh water is in the form of what we call surface water, that is lakes or rivers or streams. You might not think that when you're living in New Orleans and the Mississippi River is running by you, but the fact is that a very tiny fraction of the fresh water that is on the Earth's surface is actually what we call surface water. And that's really what we use mostly as humans. We've always depended upon surface water in rivers and streams and lakes for civilization. So this is just a chart which gives some actual numbers to that previous figure, talking about the volume in terms of cubic kilometers of water that's in the oceans, water that is in permanent ice or snow cover, groundwater, and then surface water such as rivers. So these are simply some numerical values to support that figure that we just looked at. So we're going to start off our discussion of water with talking about what's called the water cycle, or the hydrologic cycle. And the idea is that the total amount of water that's available on the Earth is fixed. We don't really do things to change water into other compounds. Yeah, there's a few chemical reactions where we can take water, for example, and we can make hydrogen gas out of water, or we can take that water in photosynthesis and make a carbohydrate out of it. But that's a very, very tiny amount compared to the total amount of water that's available. So most water molecules aren't being changed from water into some other molecule. What they are doing, though, is that they are moving from one compartment to the other. So if you're an individual water molecule, you might be in the ocean sometimes, you might be as water vapor in the air sometimes, you might be rainfall or snow or ice sometimes, you might percolate into the ground and become groundwater, but you're still a water molecule. So the idea of the hydrologic cycle is how water moves from one compartment to the other. And here's just a figure that shows the hydrologic cycle. So if we start off with water that's on the surface, either in surface water, or sometimes we have water that's in plants, and water we call it evaporation when water goes from the liquid form to the gaseous form from surface water, from a lake or a river or the ocean, for example. That's called evaporation. But plants can lose water as well, and it loses the water through the leaves, and we call that transpiration. It's kind of like evaporation from a plant, but it's given a different name. It's called transpiration. But it's the same idea. We're going from liquid water to water in the vapor phase, and so the combination of evaporation and transpiration is getting water up into the atmosphere as water vapor. And then it can condense to form small particulate forms of water, which we call clouds, and then ultimately that water can precipitate, and it can precipitate as either rain or as snow or sleet in the form of ice, for example. But it can precipitate, and it can precipitate either over the oceans or it can precipitate over land. When it precipitates over land, then we can get runoff, so the water that is falling from the air in terms of rainfall can ultimately end up in a river, and then that river can transport that water to the oceans ultimately. Or the other potential is that the water can infiltrate. In other words, it can be absorbed by the ground and become what we call surface water. We're going to talk about what surface water is in a minute. So that's the hydrologic cycle. Now, if we want to take a look at the next slide, we can see some numbers associated with that. So we've got a couple of different places we can start, but let's start right here. Let's start with this 425,000 cubic kilometers of water that is evaporated from the ocean. So much of the sun's energy is being used to evaporate water. A tremendous amount of the sun's energy is being used for that purpose. And since the Earth is 70% covered by water, most of the evaporation that's occurring is occurring from the oceans. So this is a process where we take water that's contaminated, that is salty water that's in the ocean, and as it evaporates, it leaves that salt behind, so we get fresh water. And 425,000 kilometers per year are evaporated from the oceans to form fresh water in the atmosphere. Now, about 385,000 cubic kilometers of that water simply falls back to the ocean as rain. So that's not a whole exciting kind of process. It's evaporating from the oceans, it's falling back into the oceans as rain. So it's fresh water for a while in the atmosphere over the oceans. It falls back into the oceans and becomes salty again. So that's just a kind of a closed loop. But the difference between 425,000 and 385,000 is 40,000 cubic kilometers of water. And that's the water that moves, it's evaporated from the ocean, but it doesn't fall back to the oceans as rainfall. It's transported to land. And now it's going to fall back to the earth as either rain or snow over land, not over the oceans. And when it falls back over land, that's when we can use it to do something with it. And so it turns out that the amount of water that evaporates from surface water or transpires from plants into the air over the land is about 71,000 cubic kilometers. You add the 71,000 and the 40,000, and together that ends up being 111,000 cubic kilometers of water. And so over land, we have about 111,000 cubic kilometers of rainfall or snow falling back to the earth. Okay, so you can see that we're not losing anything. We're evaporating 425,000 cubic kilometers of water from the oceans. We're evaporating 71,000 cubic kilometers of water from the land surface or transpiration. And then we have a total precipitation of 385,000 and 111,000. So those things are equal. That's what we call the water cycle. We're not really creating water. We're not destroying it, but we are moving it from one compartment to another. Now, when that 111,000 cubic kilometers of water falls to the Earth's surface, what happens to it? Well, some of it is absorbed by the land, or it gets into plants and then gets transpired, but some of it goes through to rivers, which ultimately empty out into the ocean. And so you can see that 71,000 and 40,000 adds up to the 111,000. So of that 111,000 that is falling on the land, 40,000 is ultimately running off into the oceans, like from the Mississippi River at New Orleans, and about 71,000 is being transpired back to the atmosphere. And then a small amount, it's really insignificant in terms of these numbers, a small amount can percolate into the ground and become groundwater. And that groundwater then can actually feed the river flows, so it all gets linked in that sense. So the oceans are actually our ultimate sink. In other words, the reasons the oceans are salty is because when that water falls on the ground and comes off in surface runoff into the oceans, it's picking up sediments that have minerals in them, and that is what's causing the salinity in the ocean. It's this runoff that we're talking about that we're primarily using for our water supply as human beings. So if we take the total runoff and we divide it equally by the population of the Earth, we end up getting a supply, this would be a per capita supply, of 6,760 cubic meters of water per person. This is based upon the 2,000 year population. That's how much water. If we could take all the runoff, all the water that's in rivers and stuff, and divide it up equally by the population of the Earth, each person on Earth would have access to about 6,760 cubic meters of water per year. So here's how that happened. We talked about a runoff of 40,000 cubic kilometers. In this table, it's 41,022. So they kind of rounded off to the 40,000. So you divide that 41,022 by the population, and you get the average per capita water supply per person. Well, back in 2000, you divide it by about 6 billion people, and you ended up with 6,760 cubic meters of water per person. Today, the Earth's population is about 7.2 billion people. And so if you divide, but there's still the same amount of runoff, it's still that 41,000 cubic kilometers. So you divide 41,000 cubic kilometers by 7.2 billion people. And today that number is not 6,760, it's about 5,698 cubic meters of water per person. And as the population goes up, the per capita amount of water per person is going to continue to go down. Well, that's a lot of water, it turns out. That's way more than enough water for every person on Earth to have enough electricity, to have food and all that kind of stuff, everything that we need. That's plenty of water if it were equally divided among the Earth's population. But the problem is that it's not equally divided. There are some parts of the world that are very wet and some parts of the world that are very dry. So if we take a look again at this slide, we can see that here's where we got the per capita average. So we divided that 41,000 by the Earth's population, which was about 6 billion back in 2000, and we get 6,700 cubic meters of water per person. Remember that this is in kilometers, cubic kilometers, and this is in cubic meters. So it turns out there's 1 times 10 to the 9th cubic meters of water per cubic kilometer. So if you're going to do that calculation, you've got to make that conversion from cubic kilometers to cubic meters. But let's see how this is divided among different parts of the world. So here they're dividing it up into some different parts. Here's a very wet part of Africa. It's the Democratic Republic of the Congo. And if you divide the total amount of water in the Congo by the population of the DRC, you end up with almost 18,000 cubic meters of water per person. So in the DRC, that's a water surplus situation. They have way more water than is required per person for all the uses that they might put it to. But in another part of Africa, in Kenya, this is a much drier part of Africa, so the total amount of water supply is much less in Kenya. And if you divide the water supply by the population in Kenya, it ends up only being 665 cubic meters of water. That's a big difference. They're both in Africa, but one part of Africa that's much drier has only 665 cubic meters of water per person. In the DRC, it's almost 18,000. If we take a look here at North America, let's take a look at Canada. So Canada is really in a water surplus situation. First of all, they have a tremendous amount of water in Canada, and they don't have that high a population, so the per capita amount of water in Canada is 92,000 cubic meters of water per person. If we take a look at Mexico, that's much less, 3,500. Still not too bad, but quite a bit less than 92,000. If we take a look at some other places in the world that are potential problems, here's Peru at 1,400. That's much less than the world average. China has potential problems. They're only at 2,200 cubic meters of water per person. Even in Europe, you think of Europe as having a lot of water, and in general, on average in Europe, they do. Here's the average per capita amount of water in Europe, 8,500, but in certain parts of Europe, such as Poland, it's much less, 1,200, whereas in Russia, it's much greater. It's almost 30,000 in Russia. So if we take a look at this slide, you can see some definitions. We talk about water stress. We're going to use that term in different modules. And water stress is related to the amount of water that you have available and the amount of water that you're using. So just in terms of water supply, in any case where we have more than 10,000 cubic meters of water per person in that country, we would call that a water surplus. And if there's between 2 and 10,000 cubic meters of water per person, we talk about that as a potential problem. And then if it's less than 2,000, then we talk about that as water stress. So if we go back to our definitions here, we can see that in the case of the DRC, that's 17,000, that's way more than 10,000. In the case of Canada, that's 92,000, that's way more. So these are areas of surplus, okay? There's more than 10,000 cubic meters of water per person. Then if we take a look at Peru, this is 1,400. That's less than 2,000, so we call that water stress. In other words, Peru's going to have some potential real water issues. The same thing is true here for Poland, for example. Even you don't think of Poland as being a desert kind of situation, but in terms of the amount of water per capita, it's actually in a water stress situation. Mexico you think of as very dry. Of course, there are parts of Mexico that are very dry, but there are parts of Mexico that are very wet. This is talking about the average over the whole country is 3,500. So that's between 2,000 and 10,000. So that's why it's called a potential problem. So here's just the summary of these data. The average across the world is about 534 cubic meters per year in terms of the amount of water that's available. And the amount here in North America, Europe, and Africa changes. Actually, I take that back. This is water usage, okay? We've been talking in the previous slide about water supply, but we also have water withdrawal or water usage. So the average in the world is that each person in the world typically uses about 534 cubic meters of water. Now the world average is 6,700, or today it's about 5,600 cubic meters of water. So if we're using 500 and we've got 5,600 or 6,600 cubic meters of water available, then that looks pretty good, right? We're using a lot less than is available. So that's generally speaking a pretty good situation. But notice how much difference there is in different parts of the world in terms of usage of water. So the world average is 534. In Africa, it's only 181. So the people in Africa use a lot less water per person than they do on the world average. And in North America, the average is 1,373. If we take a look at China here, it's 363. You can see there's just a tremendous difference in terms of the amount of water that's used in different parts of the world. So there's a difference in supply, there's also a difference in use. Why would there be such a difference in use? Is it because the people in America are taking a lot more baths? They're flushing the toilet a lot more? What is it that's really causing that tremendous discrepancy in use? Well, it's not really domestic use. Yeah, the individual home owner, the individual person uses more domestic water in the US than they do in Africa. But the big difference is we have electricity. We use power. We use a tremendous amount of power in the US compared to Africa, for example, the countries in Africa. And power requires a lot of water. We also have a lot of irrigated lands in the US, and that uses a tremendous amount of water. So it's not that the individual's flushing the toilet more often, it's that we're using so much more water for power and irrigated agriculture than are used in the less developed areas of the country. And we'll take a look at that in a little more detail. So just as a summary here, the 25% of the world's population, let's see, that's not what here's what I want. 1/3 of the world's population, 33% of the world's population lives in areas where there is moderate to high levels of water stress. And the problem is that the amount of fresh water that's available is fixed. That's not really changing. But population's growing, so the amount of water per capita is shrinking just because of population growth. And then, even more importantly than population growth, we are seeing countries like China and India go through incredible, rapid stages of development. So 50 years ago, China was primarily an agrarian economy, and very little electricity that was available around the country, not much in the way of industry, not much in the way of irrigated agriculture. That's changed dramatically in the last few decades. And the consequence of that is the amount of water that China is using has increased dramatically. So as this industrialization process occurs, it's occurring with a tremendous increase in the amount of water. And so the projections are by the year 2025, 2/3 of the world's population are going to be living in areas of moderate to high levels of water stress. So water availability is going to be a huge issue. We had a whole section where we were talking about energy and the potential options for our energy use, but it's not just energy that we have to look at, it's also the availability of access to fresh water. Okay, here are some maps that talk about different regions around the world that are water stressed. So you can see that here we're talking about water availability, okay? And so when we say very high, that means there's lots of water available. So you can see that essentially almost all of South America is put into a very high water availability category. Now there's a few areas like Peru that are really not going to be in that category. But for the most part, South America is in pretty good shape in terms of water availability. There are parts of Africa, in Central Africa, the rainforested areas of Africa, that have large water availability areas. And then there are parts of Southeast Asia that have significant resources. All of Russia basically is in a water-rich area. But then we have areas that are really stressed, and you can see that as you get to lighter and lighter colors, there's going to be more and more stress. So China is going to be in this category of low water availability. India is going to be in the category of very low water availability. And the U.S. as a whole is in the area of mediate, but the southwest area of the U.S. is going to be low to very low, depending on where you are in the southwest. So these are kind of averages for the whole country. They're not taking into account the differences in regions. And so, again, this one is talking about vulnerability. And here they are showing that Peru is going to be vulnerable. They're talking about China being vulnerable. They're talking about India being highly vulnerable. They're talking about some of the countries that are on the southern border of the Sahara Desert being highly vulnerable to water stress. Then they've got a few places in the world, such as Canada and the Scandinavian countries, that essentially have no vulnerability to water scarcity. So let's talk about how water is used in different parts of the world, and it really varies. So we're going to divide water up into basically domestic use, that's what gets piped to your house, industry use and power generation, and then agriculture. And if we take a look at this slide, let's see here. This slide is talking about, just in a figure, we've got the three different categories here: agriculture, industrial use, and domestic use. And you can see that on a worldwide average, the vast majority of water usage by human beings is for agriculture. Something around 70% on a worldwide average of water use is for agriculture, and a lot less is used for industry. Now, when we talk about industry, that could be used for making steel, for example, or for copper smelting, water involved in those industrial processes, or for petroleum refining. But the vast majority of the industrial use that's here is for power generation, for electricity. So much of that dark blue here is going to be for power. And then the domestic use is the percentage of the water that's used in the home and delivered through your water pipes. Look at the difference, though, in different parts of the world. If we look at Africa, very little of water usage is for industry or electric power generation. A tiny fraction of the water is used for that. Whereas if we look at North America, that's the majority of the use. And the same thing's true in Europe. In North America and Europe, most of the water that we use is for industry and power generation. Then in terms of agriculture, North America still uses a pretty hefty amount, but Europe uses a lot less. So look at the difference in agriculture for Europe and the agriculture for North America, and that's because Europe doesn't have a lot of irrigated lands. So the amount of water that's consumed for agricultural use is a lot less. So there's vast differences here. Here's some numbers that are associated with that. So the slide we just looked at is essentially a figure that represents these numbers. So in terms of a worldwide average, agriculture is about 70% or 69%, whereas in Africa it's 88%. In Canada, notice agriculture only consumes about 12%. Canada doesn't need irrigated lands for the most part, so it uses only a tiny amount of its water use is devoted to agriculture, whereas it's 88% in Africa. China, here we've got 87% of water usage in China is for agriculture. Now that's going to be changing. This is actually an old slide. It's from 1987, and if you were to do that today, that number would be substantially less, because in 1987, China was just beginning its incredible economic revolution, so that number is going to really be dramatically different for China today. So this slide was just kind of summarizing these slides. In the U.S., about 40% of our water is used for agriculture, about 40% for power generation, about 8%. So here we're kind of dividing up industry into power generation and then other industrial uses. So you can see that that category that they called industry is dominated by power. Most of the water is used for power. And then about 12% is used for domestic and commercial use. Okay. These next couple of slides talk about our rising water usage. Why is the agricultural number going up so rapidly here? This is going back to the 1920s and 1930s, and the answer is that we've dramatically increased the amount of irrigated lands in that time. And so irrigated lands use a lot more water, and that's why that agricultural usage has been increasing. And then industrial usage, again, a lot of that is devoted to power. Back in the 1930s, there were a lot of places in the country that didn't have electricity. Back in the Depression, one of the things FDR did to try to stimulate the economy was a rural electrification program. He built projects like the Tennessee Valley Authority to try to bring power to parts of the country that didn't have it. So we were only using a tiny fraction of our water back in the 1930s for industry and power generation. You can see that that fraction has increased dramatically. And yes, the amount of municipal use has increased, but that's primarily due to population increases as well. And so here, again, some similar kinds of figures with some numbers on them here in terms of usage in cubic kilometers per year for agriculture, industrial use, and municipal use. The net effect of all these graphs, though, is that they're increasing. So if you take anything away from these last few slides, it's that man's use of water is increasing, and it's not just increasing linearly, it's increasing exponentially. And yet the amount of fresh water that's available to us is not increasing. So our population's increasing, the ways in which we use water are changing, and we're using a lot more for power generation, a lot more for irrigation than we used to. And so that's why these graphs are going up so rapidly. But remember that our source isn't increasing. It's a fixed number. So increasingly, our food supply is relying upon irrigation, and that is, it changes in different parts of the world, but you can see that as one of the issues that we have with increased population is how do we feed 7, 8, 9 billion people, which is what we're looking at maybe in another 25 or 30 years. And the amount of arable land is not increasing, so we have to get more food off of a given amount of arable land. In fact, the amount of arable land is actually decreasing due to land degradation issues. So how do we get more food out of the available land that we have? Well, we have more intensive agriculture. So we use more pesticides, we use more fertilizers, we used irrigation in ways that we didn't used to. And all of that is coming into increasing the amount of water usage. So the last couple of slides are taken from this blog here, and I want you to take a look at that. We mentioned the fact that on a worldwide average, about 70% of water usage worldwide is for agriculture, but that varies a lot depending on where you are in the country. There are estimates that about 25% of the world's food supply is grown in areas of high water stress. If you take into account irrigated lands, if you add irrigated lands as part of those high water stress areas, it increases to about 40%. So about 40% of agriculture right now that's going on in the world is occurring in areas of high water stress. And climate change is predicted to increase the number of areas that are susceptible to water stress. So this number potentially can go up as the effects of climate change continue to make themselves known. There's some interesting data here in this slide that talks about the amount of water that different crops use. And so I've extracted a couple of these examples here on this slide. You can see, let's go ahead and go to this slide and we'll see where we get the numbers from. So 57% of cotton is grown in areas of the world of high or extremely high water stress. And 43% of the wheat is grown there. The rice is much less, it's only about 29%. And we get down to soybeans and other kinds of oils and it's even less. So that's one thing, is that we are growing certain kinds of crops in certain areas of the world where water stress is a particular problem. I want you to go to this website and take a look at this particular map. And I think what I'm going to do is to see if we can get to it here on the slide. See if we can open up this website. Hopefully we can. Let's see here, just a minute. Well, I seem to be having trouble. Sorry about that. Well, I'm just going to ask you to go to this website and open it up yourself. So what you see here is a map that's illuminated, and you can click on these different crops. So you can click on coffee, you can click on cotton or rice or wheat, and you can see the different parts of the world where that crop is grown. And then in the corner, you can see a little inset that talks about how much water is used to grow a ton of that particular crop. So you can see which of these crops are more water intensive, which require more water to grow. And that, I think, will be an interesting little experiment for you to do. So let's talk about the United States here for just a minute. In the U.S., we withdraw about 410,000 million gallons of water per day. So we're using that either from surface water or we're getting it from groundwater. About 80% of that withdrawal is from surface water, and the U.S. uses about 20% of its water from groundwater. In the way that that's our sources of water. The way we use it, we use about 80% of that water for both agriculture and power. So if you combine those two, that is representing about 80% of our water usage in the U.S. is used for either agriculture or to generate electric power. But it turns out that we actually use more, way more, of that water to generate electric power in the U.S. than we do for agriculture. That's not going to be true in Africa. They're going to use way more of their water for agriculture than they do for electric power, but it is true for the U.S. About half of our surface water withdrawals are for electric power generation, and about a fourth are for irrigation. And then if we look at the amount of water that we're pulling up from the ground, about 2/3 of that groundwater that we extract is used for irrigation. So here's some figures from an EPA, or actually a USGS website. On the top here, you see the total freshwater withdrawals, and here you see the total water withdrawals. So the difference here is that in some areas of the country, particularly in California and Florida, we use saline water from the oceans for power generation. So we can use that for cooling purposes. So you can see that that's the difference here. 201,000 versus 143,000. That's the difference between the total water and the total fresh water. So sometimes in thermoelectric power generation, we're using some salty water, but these other numbers are the same. So for the public supply, we don't use salt water. For domestic uses, these are the same, 3830, 3830. For agriculture, irrigation, it's 128 in both cases. So the difference here is primarily going to be that we do have some usage of salt water for generating power as a coolant. And then this is interesting down here at the bottom because it talks about the relationship between groundwater and surface water. So in terms of power generation, it's almost all surface water. Very little groundwater would be used for power generation because basically all we're doing is evaporating. So groundwater is a precious resource. We don't want to just use it for evaporation purposes. But when we talk about irrigation, it's a different story. In the case of irrigation, about 42% of the groundwater that we withdraw is used for irrigation, and the same thing here for livestock. To support livestock, about 60% of livestock are using groundwater for their survival. So those are some interesting data here, I think, in terms of water supply and water usages. We'll have some additional modules going up here shortly dealing with other aspects of water usage. So that'll finish our module then today.